So last time I showed how to calculate the topological entropy for a self-map of the interval using the Milnor-Thurston kneading theory. And some aspects of that theory are a little complicated and non-intuitive, like why does the kneading determinant's roots contain information about the entropy of the map? Maybe we'll see that later in this video, but I want to give a more intuitive approach using something called Hofbauer towers and the canonical Markov extension of an interval map. So we'll start with what are called Markov maps. So let me move myself over here. So Markov maps are one-dimensional maps that have a particularly nice property. Okay. And I won't give a formal definition, but I'll show you what it looks like to have such a map. So I'll draw my usual cobweb diagram. I won't actually do iterates of the points, but it will be clear what the iterates are, what the orbits are. Now I'm going to draw the graph of this map. So we'll say this is x down here, and this is f of x over here. And maybe the map looks something like this. Okay. So the important part of what makes this map Markov is the critical points. Where do they map? Well, this one, that maps to this endpoint of the domain. And the other one maps to itself. It's a fixed point. Here. So each of the critical points maps to either a critical point or to an endpoint. And the endpoints themselves, this one maps over to here, and the other one maps to here, which is a critical point. So it's well behaved. Now, I can also think of the laps of this map. All right, so we have 3 laps because we have 2 critical points. So lap 1, we'll call that I1. Lap 2, we'll call that I2. And then we've got lap 3. I3. Now, let's ask, where do those laps map to? Well, I1, if I can actually draw some guidelines here to make it a little easier to see what's going on. So this is where the first critical point is, the second critical point's here. And then I can ask, what are their pre-images? So I can partition the codomain by the critical points as well. Okay. Now, you can see that lap 1 maps onto all 3 of the laps. So what I could say is f of I1 is I1 union I2 union I3. Now, I2 does not map onto I3, right? Because this is I1, this is I2, this is I3. So it only hits I1 and I2, and it covers them. And I3 has the same image, I1 union I2. So it's particularly well behaved. None of the laps maps onto only part of some lap. It always maps on to a union of the entirety of some set of laps. So this is the property that we need to say that this map is Markov. Now, you don't have to map exactly to the endpoints. It could be that the core of the map, which is defined by the maximal critical point and the minimal critical point, their forward iterates could define a restriction of the domain that you could consider on which the map is Markov. So you don't strictly need this criterion about the endpoints mapping to somewhere or the critical points mapping to the endpoints exactly. It could be the case. I could extend the domain here to something like this, and it still would be a Markov map because you can restrict the domain to some subdomain on which you have this Markov property, considering the way I said it, the endpoint characterization. Now, in 1980, Gurevich and Schlenk proved the theorem that the dynamics of this map in some deep way are connected to a graph, a digraph. And that graph is determined by this behavior. Now, what I'm saying is I should put these laps as vertices in this graph. So we'll call this a Markov graph. So I'm going to make I1, I2, and I3 be the vertices of a graph. And the edges are just coming from a particular lap. What laps do you map onto? You should assign an edge for each one of those onto relationships. So I1 maps onto all 3 laps. So it should have a self loop because it maps onto I1. It also maps onto I2. And it also maps onto I3. I2 maps onto I1 union I2, so it should have an edge to I1. It should have a self loop. And I3 maps onto I1 and I2. Now we can consider the adjacency matrix of this graph. So A equals, should be 3 by 3 for this graph. And this will be I1, I2, I3 for the tail of the arrows, the edges. And for the head of the arrows, you'll have the columns. And from I1, you can map to anything, so you should have 1, 1, 1 in that row. From I2, you can map to I1 or I2. And I3 should be the same as the second row. So this is the adjacency matrix for the Markov graph for F. And maybe we could denote a little sub F there if we want. Now, they proved that the topological entropy of F is equal to the natural log, or whatever base log you want if you want to talk about entropy in different units, of the spectral radius of the adjacency matrix of the Markov graph AF. Now, what's the spectral radius? Well, you compute the eigenvalues of AF. You can do this by considering the characteristic polynomial and then finding its roots. Or, I can recognize that this is a rank 2 matrix. This row can be killed off by Gaussian elimination, subtracting row 2 from it. And then row 1 can't be killed off by any Gaussian elimination. So one of the eigenvalues should be 0. So we'll say the spectrum of AF is the set of eigenvalues. One of them is 0, and if you calculate the spectrum, you find that one is 1 minus root 2, and the other is 1 plus root 2. And the spectral radius of AF is the maximum among eigenvalues in the spectrum of moduli. So the modulus of the eigenvalue, because you could have a complex eigenvalue. So, you look at the complex plane, you plot your eigenvalues. So this is the real line. This is the imaginary line. And you, in this case, would have 0. Root 2 is bigger than 1, so you'll have something over here. That's this one. And then you'll also have 1 plus root 2 over here. And so you look at the moduli, which are the distance from the origin, and the blue one, 1 plus root 2, happens to be that maximum modulus. So in this case, we have natural log of the absolute value of 1 plus root 2, or just 1 plus root 2. So we know how to calculate the topological entropy. It's very easy for Markov maps. But this only works when laps map onto unions of other laps, and they completely cover them. If a lap maps only partially into one lap or onto a part of one lap, then you don't have this ability to calculate the topological entropy this way. Now, you could ask, aren't the images of the laps determined by where the critical points go? Because those are the endpoints. And so you could maybe try to refine this partition into laps, the lap partition, by introducing the points that lie in the forward orbits of the critical points to the partition. And yes, maybe this works, particularly if maybe the critical points are eventually periodic or something like that. So what I'm saying is, if you have another map, let's look at a unimodal map. Maybe make it steeper. Something even steeper than that. So something like this. You can ask, well, yeah, I know I have a lap partition. So this is I1, this is I2. But this interval doesn't map right onto, like I1 doesn't map onto any union of laps, and I2 doesn't either. So what do we do? Because this point right here isn't a critical point or an endpoint of the domain or anything. And no restriction of the domain to a subdomain is going to give us the Markov property. So you could ask, okay, well, I have this point. Try to introduce that to the partition. And now you get another lap. A lap, so to speak. Or another, you get a refinement of the partition to 3 intervals. And then you could keep going, and you could ask, okay, well, go here. So this turns out to be another one that you have to split on. Then you get 4 laps, I1, I2, I3, I4. And you keep doing this. And if after finitely many iterates of the critical point, it converges to, or not even converges, but directly hops on to some point that it was at previously, so it becomes periodic after a certain number of iterates, then yes, you can certainly build up a Markov graph. And then you have to think about where the laps go themselves. You have to write down the Markov graph associated to that. But in general, this is actually not possible, right? Because if you have a chaotic map, in particular, if you have a map that has the critical point bouncing around densely in some interval. So let's say maybe on this interval, eventually the critical point, the iterates of it, fill this interval in densely. Then no matter what kind of subinterval partition you try to create for the domain, denseness of the critical orbit is going to mean that when you construct intervals in here, in this part, the critical point is going to land on the interior of the interval after a certain number of iterates. And so no matter what partition you create, it's not going to capture all of the critical points at the boundaries of the partition intervals. So there's no chance that we can build some kind of Markov graph in this case. So the space is not, in some sense, separated well enough for us to, with respect to the critical itinerary or orbit, to build a partition that lets us use Markov graphs and the Mezherovich and Slink theorem. But also in 1980, Franz Hofbauer came along and he proposed an alternative approach. The same idea behind it, but a little more clever, I guess. So he's proposed that instead of partitioning the interval, the domain of the map, why don't we construct a separate space that is more nicely behaved than the interval and lift the dynamics of the interval map F to that other space. So he proposed that we build Hofbauer towers. And it turns out that actually there will be a Markov graph for these. So how do you do this? Well, we'll do it over here. So let me get an example. Okay. So let's build this map. It's going to be unimodal. We want to deal with a nice case first. I think that's the same. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Good enough. Now I'm going to draw the cobweb first because that has the data in it that I need, and I can't construct a graph that will automatically have a certain cobweb in it a priori. Maybe someone can, but I'm not good enough at drawing to do that. So I'm going to call the critical point C. And I'm going to write down the numbers on here. So what I'm going to say is we're going to define F in C. We're going to define that point wherever the nth iterative of C is. We're going to call that Cn. And I'm just going to write down the n for each one of those in this diagram. I'm not actually going to write C sub whatever the number is. So at the critical point, we must be at a maximum. It could be a minimum, but I'm going with a maximum in this case. So this is 1. The second iterate must be a minimum if we are in a unimodal map and we want it to be chaotic. Let me fidget with it until it looks right. So we'll call this 2, C2. Now we've got C3, and that's going to be just in between 2 and C. C4 lies between C and C1. C5 lies just below that. C6 lies above C4. C7 is above 2 and below 3, closer to 2 than to 3, or closer to 3 than to 2. Let's draw that right. Fix these a bit. Oh, that one's not vertical. Perfect. So that's C7. Now C8 lives just to the right of C. C9 just to the left of 1 and to the right of 6. Ten between 2 and 7. Let's just do this. And 11 between 3 and C. You can already kind of see that this is unimodal. 12 between 4 and 6. And then 13, and I'll stop here, between 11 and C. Too far down. I'll write that above. Okay. And, you can draw an approximation of what the map ought to look like. Something to this effect. This is the critical point, so that must be exact. Something like this. So this is f of x, and this is x on the horizontal axis. So I would probably claim that this will densely fill in the interval between C2 and C1. That's unjustified. I'm just guessing from how this map looks. So probably we're not going to get a good Markov partition for this. So we've got to use some other approach. So this Hofbauer tower approach is going to be hopefully our saving grace for this. So the idea is this. Write down the order of the points. C2 comes first, C10 next, C7 next, C3, C11, C13, C8, C8, C5, C4, C12, C6, C9, and then C1 at the end. And I'm going to bring it down here. That's, in fact, all the information we're going to need. So already we're kind of requiring a little bit more information than we had in the Milnor-Thurston picture, where you just needed to know what lap each one of the iterates lands in. Because I need to know, in this case, what the relative orders between the points are. If they're in the same lap, I still need to know which one is on which side of the other to construct this tower. But it turns out that for the kneading sequences, you can use the monotone sign of each of the monotone pieces of the map to reason about what the relative orderings of the points are, because you get assigned lexicographic ordering on kneading sequences. So really these are equivalent in some sense. But as far as the construction goes, to get a Hofbauer tower, I'm going to need the relative orderings of the points, and that's important. So the first thing I'm going to do is I'm going to write down a line, a vertical line. And let's see. I don't know how tall it's going to be, but we can adjust it later if we need to. And I'm going to write under that, I'm going to write C. And I'm going to draw my interval. We'll say it's 0 to 1. And I'm going to write, we'll save that for next. I was going to label this interval, but we don't need to. I mean, you could call it I or something. But next, above that, I'm going to draw C1. So C1 lies between C and 1, closer to 1. Maybe right here. And I'm going to draw a line between C and C1. And I'm going to call this interval D1. The next thing I'm going to do is I'm going to write C2 above. So maybe that's here. And then I'm going to write C3. Where is it? It's here, between C2 and C, roughly halfway. It doesn't matter where exactly it is. I mean, you can draw it accurately and you'll be able to talk about some things that you wouldn't be able to otherwise, but I'm just going to draw it roughly where the ordering suggests it should be, so the points are nicely spaced. C3's there. C4, that's between C and C1, almost exactly, just a little bit to the left of the middle, the midpoint between those two. So C4. C5 is just to the left of C4. C6, that's between C4 and C1, dead center. C7, just to the left of C3. And make sure these are all on separate levels and height-wise. C8, just to the right of C, between C and C5. Maybe a little lower. C9, over here between C6 and C1. C10 between C2 and C7. C11 is between C3 and C, closer to C3. C12 between C4 and C6. Let's bring it down some. And then C13 lies between C11 and C. Okay. And for each of these points, I'm going to build an interval. So C2, I'm going to call the interval associated to that D2. Then D3 for C3, D4, D5, D6, D7, D8, D9, D10, D11, D12, and D13. And this would continue on forever, upward. Now I do a little rule where I'm going to say that these are all closed intervals. Should I use blue for that? Let's use yellow. These are all closed intervals. And I'm going to ask, is C in the interval? Is it in D1? Well, it is. It's precisely the endpoint. So whenever that happens, on the next level up at D2, I'm going to write C1. And then I'm going to connect the 2 points, the 2 endpoints, by a line segment. C1 again. Now, let's ask, does C cut D2? Does it lie in the interval? So we're saying, does D2 contain C? It does, so I write C1 again. And let me double check. Okay, this is right. I was wondering if D3 should contain the interval or not, but it does. So you write C1. Now, this contains C, so we write C1 again. And this doesn't. D4 does not contain C, so 4 is not a cutting time. That's what we'd say. 1, 2, and 3 are, but 4 is not. Now, what we do to figure out what the next interval should be is you should think of these intervals that aren't at cutting times, they're not being cut by C, as being true intervals in the domain of the map F. And this interval, D4, lies entirely on one side of the critical point. And so it lies in a monotone piece of the map F. So it should be, let's ask what the image of D4 is. So F of D4. So that's F of the closed interval from C4 to C1. But because F is monotone on this interval, we can just iterate the endpoints and get the new interval that is the image of that interval, the original one, C4 to C1. And because the map is decreasing on this right side of the critical point, I know that I'm going to have to flip the endpoints when I iterate them under F. So this should be equal to the closed interval from F of C1 to F of C4. But we know what those points are. Those are C2 and C5. Just increment the index. Well, you can already see that C5 is on the next level. So just draw. And I should be doing yellow for these. And this. So I just needed to write C2 now. Well, C2 was here. So that gives us D5. So at the times when you're not at a cutting time, you just iterate the whole interval that you're at forward one time. Now this is a cutting time, so of course I'm going to write C1 again. Maybe I should color these better too. And then we just connect with the line segment. This is not a cutting time, so I'm going to iterate this critical point. C2 is what I get. So that's D7. And Dn, it always contains Cn as one of the endpoints. So this is not a cutting time, so I should iterate once more the old point, right? The one that is furthest back in the orbit of C. Because I already know what the newest one is, it just goes to C7. So C2 goes to C3, so I write C3 here. And we just continue this process all the way up. This is a cutting time, I write C1. And you'll see why we're doing this shortly. C2. Oops. C3. C4. That was here. So let me make it easier for myself. and then C5. And we would continue on upward. What's going on at the cutting times? Why are we doing the thing where we write C1? Well, notice something. D1 is a cutting time. But D1 maps precisely onto D2, right? Because C goes to C1. C1 goes to C2 on the left side. Let me highlight. So this point goes to this point. This point goes to this point. And the entire thing does lie on a monotone piece, even though the critical point lies at the end. Because you don't actually extend into the increasing part. So you can't have any kind of weird behavior with f taking intervals to things that aren't just intervals with endpoints being the iterates of the previous endpoints from the pre-image interval. So D1 maps onto D2 onto. But what happens to D2? Well, look at the new part, the part associated to C2. So you partition, you do a lat partition of D2. Well, C2 goes to C3, and C goes to C1. So D3 is the image of this part. Likewise, for D3, if we want to ask where this part associated to the newest endpoint goes, it's C3 goes to C4, C goes to C1. So this just goes up to here. Up here, this guy, C to C5 goes to C1 to C6, or C6 to C1, and so on. So the side that has the newest endpoint is nice. We know it just goes up one level in the tower and it covers that whole interval. But the old side, the side associated to the oldest endpoint, where does that go? Well, here for D1, that's C to C1, which is precisely D1. So that must map onto D2. So this guy maps onto here. What about up one level above, the old part of D3? Well, that's here, that's the same interval, so it maps onto C2. But this doesn't always happen, it can be different. Notice that D5, the old part, well, where does that map? It goes C3 and C, which is D3. All right, because C2 goes to C3 and C goes to C1. I should have said C3 and C1. So it goes on to D3. And up here, it has C3 at the endpoint, so it should go to D4, right? Well, it's C3 to C, so it should go to C4 to C1, and it does. That's D4. Up here, the old part is C to C5, so that should go to C6 to C1, which would be D6. So it behaves nicely. Now what you'll notice is the new part always goes up. One level in the tower covers that entire dn. So if you're on dn at a cutting time, you go up to dn plus 1 for the new half, if you're at a cutting time. And for the old half, or the old part, you always go back to some previous cutting time, actually. Or some, that's not right. I should say you always go back to some previous interval that was one time after, like one iterate after a critical cutting time. And why is that? Well, it's always going to have C1 in the boundary as an endpoint. And the only way that can happen, because C1 is the maximum in the image of F, and you presumably have a nice map that doesn't have a like constant critical point, like you don't have a flat top or anything. There's only one point that goes there, and that's C. So you had to have come from C. So what that means is this has to be 1 after a cutting time. So anytime you have a cutting time, the part that gets demoted in the tower, that goes downward, or maybe goes back to itself, back to the same level, where it goes has to be 1 plus a cutting time. And we'll see that this really matters here in a moment for our build-up of the what we call canonical Markov extension. So I'm going to give a couple of things that we write down when we compute a Hofbauer tower. So this is the tower, like we've constructed it. But there are 2 pieces of algebraic data we're interested in when we compute these, or when we draw them. The first datum I'm going to write is, I'm going to write the cutting times. And I'm going to do this in kind of an odd way. I'm going to write the very first one I'm going to call S sub 0. And that one's always 1. D1 is a cutting time, just because of the way we've constructed this Hofbauer tower. Now, no, if you have a non-chaotic map, maybe it won't be possible to do this, but then you just have trivial dynamics, so who cares? We just want to analyze the positive topological entropy maps and compute their entropy. And then the second cutting time, we write S1, is always going to be 2. S2, this could be 3 or 4. But in our case, 3 is a cutting time, so we write that. S3 is the next cutting time. And just notice, the map I've constructed has the Fibonacci numbers as the cutting times. So 1, 2, 3, 5, 8, and then 13. So we can just go ahead and write them. And I've constructed this map specifically because it has a nice set of cutting times. In Hofbauer towers, it turns out that the maps that have Fibonacci-like sequences as their cutting times are of special interest. There are other kinds of cutting time sets that are also interesting, but 21 plus 13, 34, and so on. So that's one piece of information I need to know about this Hofbauer tower. Now the other piece is, well, I have to say something before I talk about that. Look at the difference between any 2 cutting times. So take a cutting time sk, just k is any natural number, and subtract from that the previous cutting time, sk minus 1. My claim is that this always has to be a cutting time. And you'll get some intuitive sense of this, especially when we talk about the multimodal Hofbauer towers. I won't say exactly, I won't prove it, but you should be able to reason that out and see that it must be true if you play with this enough. So that's a cutting time. And what is the index of that cutting time? Well, it could be a lot of things, but I'm just going to take whatever it is and say that it depends on k in our map. So there's some function associated to this map f that takes k and tells me what that difference of 2 cutting times that were consecutive was. It gives me the index of the cutting time that I get from asking what the difference in cutting times was. So let's go ahead and compute this q of k. Because we have to be able to take k minus 1 for a cutting time, k minus 1 can't be less than 0, so certainly k can't be less than 1. So we ask, what is q1? Well, you have this. K is 1. K minus 1 is 0. So q1 should satisfy this. Well, s1 is 2. S0 is 1. So that's 1. So that's what sq1 has to be. And so q1 has to be 0. So what I've done is I've said, in your head, What's the difference in these two? It's 1. What cutting time is 1? Cutting time 0. That's the kneading map value for 1. So we're calling Q the kneading map. Q2, what's 3 minus 2? That's 1. S0 is 1, so we write 0. Q3, what's S3 minus S2? It's 2. So I get 1, because that's the index of the cutting time, that is 2. Q4, difference is 3. 2 is what I get. Q5, Q5, S5 minus S4 is 5. Cutting time associated to that number, or that is equal to that number, is cutting time 3. 6, the difference is 8. 4 is that. My claim is this will be 5. They're just increments. So in fact, we have Q of K is the maximum of 0 and K minus 2. In this case, this only happens for this particular map, and a few others that are entropy equivalent to it. Alright, so why do we care about this? Well, you notice that I only need to know the cutting times, so I only need to know the cutting times in order to get the kneading map values. And I'll claim that the opposite is true. I can give you a kneading map and you automatically know what the cutting times are, because we know always that S0 is 1 and S1 is 2. So then the differences can be determined by the kneading map. And then you can just iteratively construct what all the cutting times are. But that's not interesting in its own right. So, you know, the kneading map is like this nice thing that gives us the cutting times. But then how does this relate to the map itself? What does it tell you about it? Let me look to make sure I'm saying this right. So we do have a theorem. It turns out if Q is bounded, then the omega limit set of the critical point is nowhere dense. In fact, if you want to, you can show that this is a good exercise. You can show, and you'll see how to do it shortly, like you need a extra piece of information here in a moment. You can show that if Q is eventually constant, then the kneading sequence associated to the critical point is eventually periodic. So if you're in a compact interval, right, like 0 to 1 closed, if you have forward iterates of a point being nowhere dense, aren't you eventually periodic? So the set of points is finite, because any infinite set of points in a compact interval is it accumulates somewhere, has a limit point. So on the other hand, if Q is unbounded, then C is persistently recurrent. So it comes back. You can put an arbitrary neighborhood around it, around C, and the itinerary of C will come back to that neighborhood infinitely many times. And also, the omega limit set, which is the set of points, it's almost like a lim soup. It's the set of points in the domain that the orbit of C never stops coming to a neighborhood of, an arbitrarily small neighborhood of. So the omega limit set of C is a minimal Cantor set. And we won't talk about the Cantor set view on attractors of one-dimensional maps in this video, but that's the theorem. Another theorem this is the admissibility criterion for kneading maps. And what does that mean? It means if you give me a kneading map, I should be able to construct the cutting times from it. But it's actually possible that you constructed a kneading map where there's no way to reconstruct the cutting times because you need this property to be satisfied. And that can fail if you just give me an arbitrary function as the kneading map. And also there can be no map, no unimodal map that has the particular kneading map that you hand me. So the admissibility criterion says which kneading maps actually correspond to unimodal maps of some sort. And that is twofold. There exists F with kneading map QK if and only if two things are satisfied. One, QK is less than K for all K. And two, this kind of strange condition. Q of K plus J for all J greater than or equal to 1 is greater than or equal to, under what we call the lexicographic ordering, and really this should be a sequence, but sometimes people don't write it that way. Q of Q squared of K plus J. For all J greater than or equal to 1. Now it's a little strange. What is this? Well, this is sequence. Q. And this should be for all K, right? Q, K plus 1. Q, K plus 2. Q, K plus 3, and so on. This should be greater than or equal to in the lexicographic ordering. Q, Q squared, K plus 1. Q, Q squared, K plus 2. So on. And so the lexicographic ordering just says either this is greater than this, like strictly greater, or if they're equal, you look at the next one. So it's the dictionary order, right? And then if that one's greater than, if this one's greater than this, then you're still good. or if they're both the same, you go to the first place they differ and you ask, is the left one greater than the right one? This one greater than this? And if they are, then this is true. And if they're both exactly the same all the way out, then it's still true. But if you go to the first place they differ and the left one is lesser than the right one, because these are natural numbers, remember? If the left one is lesser than the right one, then this property isn't true, and so you wouldn't have an admissible kneading map. So I should have written an equal sign here. So that's the admissibility criterion. And this, we'll see shortly, this will actually tie in very closely to kneading sequences and admissibility criterion for those. But I won't lay it out because it's going to take too much work, and you can kind of do it on your own as an exercise if you're interested. It's just, I just want to point out that relationship is there. These two can be translated between each other. I don't know, this has nothing to do with cutting times. I'm only talking about the kneading map itself. Right? So we haven't used this perspective, even though I can convert back and forth between the kneading map and the cutting times. I haven't used the cutting times to talk about the admissibility criterion. No. How do you actually build up the Markov graph for these unimodal maps if you have this Hofbauer tower? That's quite easy to do, actually. Remember, we had the property that every level of the Hofbauer tower goes up to the next level. Like it maps each interval, D3 for example, maps onto D4. But it also maps onto something else lower in the tower, or at the same place as itself. So certainly, every interval maps up, because even the ones that aren't at cutting times, they also map up. So I'm going to build the Markov graph with the dn intervals being the edges, or excuse me, the vertices. And I'm going to establish what they call the action on the Hofbauer tower. So the Hofbauer tower itself is the Markov graph. We just have to put edges on it, and they call that the action on the Hofbauer tower. The edges are. So you have two relations you need to know. dn for any n has an edge to dn plus 1. Okay, so that's one of the two possibilities that you could have for an edge. The other is at the cutting times, ds sub k. You can map down or back to the same interval. And what k is actually determines where you go on the old lap in your interval dsk. ds sub qk plus 1. And the plus 1 is added to the cutting time, not to the index of the cutting time. Okay. Now, this is related to what I was saying earlier, because the cutting times, the part that goes down, well, that part, before it goes down, it has C in the boundary of it, that subinterval. So certainly it must map to something with C1, because it lives in a monotone piece, because you're doing a lap partition of dn, or dsk. So it has to map down to something with C1 in the end as an endpoint of that interval in the image. So that will be S sub qk, so it's a cutting time plus 1. So that's where that comes from. Right, so we can just go ahead and construct this. We know our cutting times and we know our kneading map. And in fact, this rule uses both, so you actually do need both to build up this Markov graph. You have D1, D2, D3, D4, D5, D6, D7, D8, D9, D10, D11, D12, and we stopped at D13, but it keeps going up. And you have ascension at every level. But you also have the down edges, the backwards edges. So those happen at the cutting times. So that's 1, 2, 3, 5, 8, and 13. And where do you go? Well, look. Let's look for k equals 1. So dsk, k equals 0. Well, we won't have that for 0 because the kneading map isn't defined there, right? But we will have it for k equals 1. So that's S1 is 2. So we're going to talk about D2. And that maps, because k is 1, it's going to go to D. Let's just write it out. ds1 goes to dsq1 plus 1. But ds1 is d2, right? And what's q1? That's 0. And what's S0? Well, that's 1. So that's D2. So D2 should have a self loop. Just for taste reasons, I'm going to draw it backwards so we're descending. What do I have for k equals 2? ds2 goes to dsq2 plus 1. But S2 is 3. So D3. And SQ2, well, Q2 is 0 again, so we must go to the same place that we went last time, which was D2. So D3 goes to D2. What about the next one? ds3 goes to dsq3 plus 1. Well, ds3, S3 is 5. So d5 goes to q3 is 1. So ds1 plus 1. But s1 was 2. So d5 maps to d3. And it won't always be like this. It won't just map down 1. It can go down further. But in this nice map, it's going to do this. I'm going to guess that d8 is going to go to d5, but let's just check it. So we looked at k equals 3 last time, so we're going to look at ds4, and that goes to dsq4 plus 1. That's d8. This is going to be well, q4 is 2, right? You just subtract 2. But s2 was 3, so this is d4, or sorry. S2 was what? 3. So that goes to 4. So it's a little bit different from what I was saying, right? Because it has to be 1 plus a cutting time. It can't be any other way. It's not necessarily going to be on a cutting time unless that cutting time had one directly preceding it. I'm going to guess D13 goes down to, say, D6 or something. let's check. ds, what did I do last? We had 8. So S4 was 8, so we're looking at S5. And that's 13. Q5 is 3. S3 is 5. So 5 plus 1 is 6. And sure enough, 13 goes to D6. And that works. Now this is actually a Markov graph for F, which is that unimodal map we started with, the Fibonacci map up here. So assuming that this Fibonacci sequence continues in the cutting times, then the kneading map will continue to be k minus 2 for every k. And because of that, we can continue to build up this, what we call canonical Markov extension, which is this guy. And now the question is, does the result of Gurevich and Slink about the topological entropy of F carry over to the canonical Markov extension? Well, it's not clear, right? Because we're going to have countably infinitely many intervals in our Hofbauer tower. And so the adjacency matrix of the Markov graph, or the Markov extension graph, is not going to be a finite matrix. So we can't write out the matrix, compute the eigenvalues, and say that the largest modulus one, its modulus is the exponential of the topological entropy. But what we can do is we can say, hey, truncate the tower. Just end at 13, let's say. Get rid of anything that goes higher. Kill that off. Don't talk about further ascensions. Build the Markov graph that only goes up to 13, has all the other edges besides the one that elevates up above, or anything coming from higher, and compute the adjacency matrix. I won't do it, but just because it's going to take a minute, but I can easily do that. I can look at this graph and I can say rows 1 through 13 correspond to D1 through D13, and so do the columns 1 through 13. Just write a 1 or 0 depending on whether there's an edge at the corresponding two vertices going in the right direction. And then compute the spectral radius of that matrix. You get an approximation of the, well, I'll say you get a spectral radius. And so I'm going to say if you truncate to n, to dn, so write row n, in fact let's do this, call an adjacency matrix of canonical Markov extension truncated to just be the vertices, so this is a subgraph, D1, D2, up through Dn. Let row n, in fact, this is fine. The claim is, and I don't remember the error bound on this, there's a paper by Henk Bruin that says what the error bound is in the limit for large n, but the claim is Gurevich proved for these countable Markov graphs he showed that the topological entropy, I won't say of F, he showed it for the Markov maps, themselves, or for the Markov graphs themselves, but I'll say for f, just kind of hand-waving here, this is the limit, as n goes to infinity, of ln of the spectral radius of an. So the same thing we had by Gurevich and Slink works for these canonical Markov extensions. And in fact, the convergence is often quite fast. The nice thing is that these adjacency matrices, because, you know, each interval, each vertex in this Markov graph only has 2 outgoing edges or 1. So the adjacency matrix is quite sparse. It's mostly zeros. And so you can, on a computer, you can represent this with a sparse matrix data type. And you can compute the spectral radius by taking a random vector and applying matrix multiplication by the adjacency matrix to it, rescaling it, whatever, you start with a vector, you apply the adjacency matrix to it, you multiply it times that vector. It changes the direction and the length. You normalize that vector after that, and then you do it again. Normalize it again. And once it converges to something, you then ask, well, applying A again, you're going to be very close to an eigenvector. So applying A again should just rescale you. And so that's an eigenvalue, whatever you get rescaled by. So you just take the length after one application. And that eigenvalue that you extract is going to be the maximal one, max modulus. And you just take the logarithm of the modulus of that eigenvalue. And that turns out to be your spectral radius, a very good approximation to it. So this is how you can compute the topological entropy of a map using the canonical Markov extension and the Hofbauer tower. Much more intuitive because you can see what the intervals are, what they correspond to back in the map. You can reason about them like an undergraduate would after taking Calc 1. And everything's nice. Now I want to say something about how this relates to the Milnor-Thurston kneading theory. Where's the... It's up here. Okay. All right. So take the critical point and write down the kneading sequence associated to the critical point. So let's do this constructively in this case. So the kneading sequence, I'm going to do it with zeros and ones. I'm going to write 0 if we're on the left side, and I'm going to write 1 if we're on the right side, and each iterate. I'm going to start by writing C, just to keep things simple. And let me make sure I do this exactly right. Yes, okay. Then I'm going to write, well, C1 lives in the right side, so I write 1. C2 lives on the left side, so I write 0. 3 is on the left side, 0. 4 is on the right side, 1. 5 is on the right side, 1. 6 is on the right side, 1. 7 is on the left side, 0. 8 is on the right side, 1. 9 is on the right side, 1. 10 is on the left side, 0. 11 is on the left side, 0. 12 is on the right, and then 13 is on the left. And this keeps going. And I'm going to add a little notation here. So I'm going to say that this sequence, this is E0, 1 is E1, E2, E3, E4, and so on. So the symbol 0 or 1 associated to each Cn, I'm writing is En. So E0 is the symbol associated to C itself, so it should be C. Because that point C doesn't actually live in one or the other lap. No. The Hofbauer tower, the data from it, the cutting times and the kneading map, imply something very strong about the kneading map, or about the kneading sequence, which was that E1, E2, so on sequence. So I'm going to claim for all j greater than or equal to 1, define this thing, b sub j, to be e sub s sub j minus 1? No. S sub j, and then the minus 1 should be in the index for s. And plus 1 to the s itself. E s j plus 2, so on, up through e s j. I messed that up. That should be j minus 1 plus 2. So what I'm saying is, go to a cutting time, sj plus minus 1. Go to the next iterate of that. Ask what the kneading symbol is. That's e sub sj minus 1 plus 1. Take all the points up until the next cutting time and extract the kneading subsequence associated to that. Call that bj. The claim is that this is equal to the kneading subsequence E1 up through E S QJ minus 1. No, that should be applied to the S itself. And then finally SQJ, but we're going to pivot the kneading symbol. So writing a bar above the E just means if it's 1, make it 0. If it's 0, make it 1. If it's C, you can't talk about it. So we can't deal with periodic orbits here. I mean, there's a way you can extend it to do that, but... And in the multimodal case, this relation actually gets fairly complicated. And pivoting has a strange structure to it. But this, turns out, actually lets us take the Hofbauer data and reconstruct the kneading sequences. So we can, if someone walks up to you and gives you a kneading map, Q, you can then take that and compute the Milnor-Thurston data, all of it, the kneading matrix, kneading determinant, everything. So we'll walk through what this actually looks like, because it's not exactly clear just yet, right? So I haven't, I did write down the kneading sequence up to 13 up here, but I didn't, I had to look at the graph to actually do that, or I had to look at that ordering of points relative to C to do that. So let's see how I could have done it from the kneading map and then the cutting times. Okay, so just remember S0 is 1, S1 is 2, so you can just take the Fibonacci numbers up above that to remember this stuff. And then the Q's are just K minus 2, basically. And if it's negative, just make it 0. So I will copy it, just so we can work with it more easily. Why is my tablet telling me this? There we go. Where's my phone? There. Okay, so let's see from this data how you would actually go about reconstructing the kneading sequence. So B1, we start with B1 because we're going to take QJ, so we can't take Q0, so we need to start with J equals 1. So let's do it in red. So B1 is E S1 minus 1 plus 1 E S1 at the end, and that's going to be E1 up through ESQ1 minus 1, and then pivot ESQ1. Well, what is this? Well, S0 was 1. Add 1 to that, you get E2. What's S1? Well, that's 2. So we stop at E2, so it should just be one kneading symbol. And it turns out I need to pivot no matter what it is. So we'll just say E2. I don't even have to ask anything about what these indices are. I just know that, and this should be E1. I'm sorry. It always has to start with E1, and it goes up to ESQ1, which is S0, which is 1. So we stop there and we pivot. So I always know in this concave down map that E1 is going to be, if we want chaos, we need E1 to be 1. So automatically we get C, E1 is 1, and then E2 has to be 0. Can we check if that was the case? C1, 0, so we're good. What about the next part? B2 is ES2 minus 1, I'll just write 1, plus 1, ES2, and that's equal to E1 ESQ2 minus 1, E pivot SQ2. Well, S1 was 2, so add 1 to that and you get 3, E3. We go up to S2, which is 3, so we stop at 3. And, well, this is E1, pivot. So E3, so that's, remember, E1 was 1, so we have 0. So we get a 0 there, and if you recall from the kneading sequence, that was what we had. Now what about B3? And I'll do probably B4 as well, and then we'll stop. Let me think. That should be good. Maybe B5, but we'll stop when it gets tedious. So this is ES, well, 3 minus 1 is 2 plus 1. ES3. E1 up through ESQ3 minus 1, E pivot SQ3. Well, we know Q3 is just 1, right? So we can simplify things. But S2 is 3, so 3 plus 1 is E4. What's S3? 5. So this will give us 2 symbols. So we should have 2. So E1, I never really need to check what this is, but you can check that. Q3 should be 2. Have I got something wrong here? No, Q3 is 1 and S1 is 2, so that's what we need. So E1 and then pivot E2, because that's where we stop. So we started with 1, 0 in the kneading sequence, so we should have 1, 1 next. Let's go back up and check. 1, 0, 0, 1, 1. So that's right. And then the last one we'll do, B4. Now notice, what are we doing? We're looking at the differences in the cutting times. Here I was looking at 4 or 5. So that's between 3 and 5. Remember, they're Fibonacci numbers where you have cutting times. So we're going to go up to the next Fibonacci number. So it should be E6, E7, E8. And that should be E1, E2, E3 pivot. Well, we had 1, 0, 0, right? So this is going to be 1, 0, 1. So let's see. It should be 1, 0, 0, 1, 1, 1, 0, 1. 1, 0, 0, 1, 1, 1, 0, 1. Good. So this lets us translate to kneading sequences. And you can work out what the backwards translation looks like. But the last thing I want to say about these unimodal Hofbauer towers is, what are the complete sets of information that we can get? It's nice because any piece of information is complete in this case. When we get to multimodal Hofbauer towers, that's not going to be the case anymore. But you'll be able to always construct a complete set of information that has no redundant information. So in terms of calculating the entropy, it's enough just to have the cutting times. So I'll say complete sets of information. As far as entropy goes, cutting times, kneading map, Q, QK, and I should write this is SK. And lastly, the kneading sequence. En. And any of these is enough to go back and forth. If you have one, you know any other. And each of them is enough to calculate the topological entropy. What is different in the multimodal case is, well, the kneading sequences, they turn out to, you need one for each critical point. And in fact, you really need 2 if the map is discontinuous at the critical points, or the turning points. 2 per critical point, I should say. But for the Hofbauer tower, it turns out that the cutting times are not enough to calculate the topological entropy. And they're also not enough to determine what the kneading sequences are. And they're not enough to determine what the kneading map is. We'll get this extra piece of information called skims. This is just what I've been calling it. And they're associated to each of the critical points. And it's just another sequence of numbers. So skim indices. And if you have those, and you also have the cutting times, then this becomes a complete set of information. The kneading sequences themselves are still a complete set of information. But cutting times need skim indices to become complete. And on the other hand, the kneading map is also not enough to do anything in terms of calculating topological entropy or translating to other complete sets. You can't extract cutting times from the kneading map by itself. You can't extract the kneading sequence from the kneading map by itself. So if you have the skim indices, you can pair that with the kneading map as well, and that makes a complete set of information. So this turns out to be really fundamental. And the reason you don't see it in the unimodal case is because it's always 1. So it's known a priori. So it never comes up. But I'll show that when I actually put out a video on multimodal Hofbauer towers. And I think that is it. Let me double check that there's nothing obvious I'm missing. Oh, another thing about the two theorems that I mentioned about boundedness and unboundedness of Q. If Q is bounded, you also have this thing where you can say F is long branched. And then if it's unbounded, you can say F is not long branched, or it's short branched. And what being long branched means is look at the width of the intervals in the Hofbauer tower as you go up each level. When you don't have cutting times, the intervals get narrower in general. In the long run, if you don't have a cutting time for a very long time, the intervals get short. Now, it isn't to say that the cutting times need to eventually stop. Like, you need to never come back to the critical point, but if the kneading map itself is bounded, then the distance between cutting times stays relatively short, and so the intervals never, they stay some, how would I put it? If the map isn't long branched, which means Q, the kneading map, is unbounded, then the intervals in the Hofbauer tower will go to zero width. And if it is long branched, that doesn't happen. So that's what that is. So this is a relatively useful thing that tells you about the topological entropy, the Hofbauer towers do, and they also give you some details about the orbit of the critical point that are not given to you by things like ergodic theory or the recurrence theorems in it, because that can only tell you about a full measure set of points, and it doesn't tell you anything about a particular point, like the critical point. Is it actually recurrent? But the Hofbauer towers can actually tell you that. You just have to compute the kneading map and ask, is it bounded or not? And if it's bounded, then you don't have the critical point being recurrent unless it itself is a periodic point. So it lies on a periodic cycle. And if Q is unbounded, then you know that you have recurrence for the critical point. So that is the unimodal Hofbauer tower construction. It gives us our canonical Markov extensions, and this idea of canonical Markov extensions does extend to other maps of different dimensions. So Buzzy, spelled B-U-Z-Z-I, has done work on two-dimensional maps and higher dimension as well, showing that you can use a similar kind of approach, but it's more involved to construct canonical Markov extensions, or Markov extensions. They may not be like unique in some sense, but he shows how to construct them for higher dimension maps, and you can compute things like topological entropy from those as well. So that's it for this video, and I think the next one will probably be the multimodal Hofbauer towers, and then we may go deeper into the Milnor-Thurston kneading theory, or if I figure out something about these Buzzy towers or something, that could be a nice topic to talk about too. All right, thank you.